Okay, so I guess you know who I am. I just wanted to show a picture of us in Nepal. We've been having a great time, and I think this was, I forget which museum this was, but yeah. Huh? The Royal Palace, yeah, okay. And yeah, it's been fun. um, so, yeah, I mean, this is I'm going to be talking about a bit of introduction first to kind of get everyone up to speed. And then I will kind of talk a lot about research topics. So we will kind of cover a broad spectrum of levels of things. There's obviously not only my work, there's a lot of collaborators around the world that contribute to this. So just a bit about what we will talk about. So we will start with graph neural networks. We will go over some mathematical background. This may be new, maybe at least some of it will almost certainly be new. And then we'll talk about GNNs. In general, I think I wanted to tie a lot of topics to current models. So I'm, like, really this talk is about tying, like, unifying a broad perspective, a broad class of models under graph theory. So in this way you can kind of get intuition from a lot of these models, but through the lens of graph theory. So let's start with graph neural networks. I will actually be writing down stuff. So just so everyone is on the same page, a graph is, you have nodes and you connect it, right? So this is a graph, and then you put a labeling over the nodes, right? So this is kind of what very basic principle, but now we want to represent it in a way that's easy to deal with computers. And usually computers are very good with linear algebra, right? So it's common to make an adjacency matrix A, right? And this is very basic, but just so everyone's on the same page. You can have the labeling, right? And then you can say, well, 1 is connected to 2, and likewise this is undirected, so 2 is connected to 1, and so on. So 1 is connected to 3, and so on, right? So you can kind of fill in this matrix, and now this matrix is literally a representation of this graph, right? But the advantage is now that computers are very good at dealing with matrices. So this is the idea. Like, in some sense, we are setting an ordering on the nodes, and like Jacob was saying, this causes some issues because we're essentially picking a basis on which we operate, but picking this basis is very convenient for computers. There's one more matrix which I'll introduce because we'll use it a bit later, and this is the degree matrix. And this is simply a diagonal matrix. So you have zeros on the up diagonals, and this will be like the degree of the nodes, right? So for example, for node 1, the degree is 2. For node 2, the degree is 1. For node 3, the degree is 1. So these matrices are kind of the very fundamental matrices that we use in spectral graph theory. The advantage is that now that we're kind of connecting them to linear algebra, I mean, linear algebra is a very kind of well-known topic in mathematics. It's a very well-understood topic, and what we will see is that the eigenvalues of these matrices are also very important. So we will be talking a bit about that later. In particular, one matrix that's very important is called the Laplacian, and this Laplacian is simply D minus A, right? And this is like a very important matrix, and we'll be going over why this matrix is important and how we can build graph neural networks out of this Laplacian. Okay. So one last thing maybe. What we consider is problems in which we have a graph, but to each graph we have a signal. So you can really view the nodes, as Jacob was saying, as the domain, and now over the nodes we have a signal which will be d-dimensional. So you can really view this as like we have some x3, which is now like in RD, right? And similarly we have an x2 which is in RD, and x1 which is in RD, okay? And then what we can do is put these all in a big matrix we call this X, and this will simply be like x1 transpose, x2 transpose, x3 transpose. This matrix is in Rn by D, where n is the number of nodes. Okay, this is all the kind of very basic setup we'll be working with today. So this is kind of just what we're saying. We can consider a graph as a tuple, and we have this kind of structure. Some examples of what graphs we usually work with. So, for example, in social networks, the nodes will be the people in the social network, and the edges will be kind of how if they're friends or something like this. And the signals will be information of the user. So how many friends they have, how old they are, things like this. In molecular graphs, we have like atoms, which are the nodes. The features could be like the coordinates of the atoms or what kind of atom they are. And the edges could be like if they have a bond, right? So similarly, we have like, if you're like Amazon, then the nodes could be products and users, and then the edges could be how these kind of things interact. Usually this last examples, they're usually called recommender systems. And these recommender system graphs are usually bipartite. So bipartite graphs means that you have kind of two different classes of nodes, and nodes from one class only talk to nodes of the other class. Okay. So graph neural networks operate over these kind of structures. So again, the domain is the nodes, and the signals are these node features. So in this work, we will be, in this talk, we'll mostly be talking about message passing neural networks. So these are a specific kind of graph neural network, probably the most popular kind, and people argue that every graph neural network can be interpreted from the point of view of message passing. We'll go over, of course, what this means. So let's define message passing. Now, this looks maybe a bit abstract, but I'll give some examples later, which maybe you've seen before to kind of ground this. So in message passing, you kind of have two components. So one is like you're considering here the node itself, and then here instead you're considering all of the neighbors, right? And neighbors are pretty much the nodes that are adjacent, directly connected to the node itself. And this aggregation function is pretty much taking a convolution over these neighbors, and this combination function is combining the information between the neighbors and the node itself. Okay. And this is known as message passing because in some way the nodes are message passing messages to to neighbors which are close. And this is a very, from the point of view of inductive bias, this makes sense because, for example, let's say you're in a social network, you probably want to, probably the users which have the most information with respect to yourself are people you're friends with, right? And then people who are friends of your friends maybe have less information. So this really kind of encapsulates this kind of structure. Just to be a bit more kind of concrete on the aggregation function, maybe you've seen this in a few talks. All you're doing is, from a linear algebra sense, is kind of using this adjacency matrix, and this is why this adjacency matrix is so convenient, because you're pretty much just kind of directly summing over this adjacency matrix, and then looping over these, you're kind of just summing over the neighbors, right? So this A can have different forms. So these are called graph shift operators. So technically, even like a Laplacian is like a graph shift operator. These are just kind of details that come from signal processing. But yeah, in general, you can just think that you can use these matrices to efficiently kind of convolve over your neighborhood. Oh, by the way, if I'm not clear on anything, let me know. Now, I just want to give some very basic models because we will be actually studying them more kind of theoretically later, so it's good to kind of know them. So probably the first model that came around, some models came around before that, but the most notorious one is the graph convolutional network. We'll be going over what that looks like. Then there's graph sage, graph isomorphism networks. The real kind of pattern is that all of these models fit within this very concrete implementation of the kind of abstract message passing form we saw before. And this is very intuitive. So first of all, what we do is we have a matrix that's multiplying your node, the node of reference. So here we're saying, how do we update node B, right? So we take a graph neural network layer. This graph neural network will update at each node the signal. So first what we do is kind of do a matrix operation on the node B itself at the previous time step. And then we also take the contributions from the neighbors. So GCN and all these models, they can actually be, they're special cases of this more general equation. And in this sense, we can really view message passing as an operator mapping node signals of d dimensions to node signals of d prime dimensions. So pretty much what we have is we have a graph, let's draw the simple graph, and now this x1 And now what we do is with this GNN is we send it to a vector in RD prime. And we do this for every node in the graph in a way that's like respecting the symmetries of the domain. And really the only symmetry in this domain that we can consider in a general case is permutations, right? So really you can view graph neural networks as doing this, like they're like by definition like an operator that operates over a graph and transforms the signal over the graphs in a way that's like permutation equivariant. Okay. I want to talk about graph attention networks because then there's like a very strong connection between graph attention and transformers. So in some way, like I would like to try to summarize like a lot of models. Like in this talk, I kind of want to talk a bit about different types of models and how they all relate to each other through this perspective of graphs. So graph attention operates in such a way. So this is the same, right? So we've seen this already, but then we have this scalar factor here. And this is called like usually like an attention coefficient. And the attention coefficient is actually very intuitive. I'll be kind of drawing this out later. But you can really view this as a way to kind of weigh the neighbors in a different manner. In particular, this attention coefficient is learned. I'll show you how. But what's very crucial here is that transformers, so this is like the very most traditional transformers, is kind of a special case of this graph attention network that you recover when this graph attention, or when the graph is fully connected. So, like as an example, if a transformer operates over sequences, so you have like the cap is, right? So this is kind of like you could run a transformer on the embeddings of these words. So you can really imagine them like, these are all nodes, and this graph is fully connected. So like everything connects with everything, right? And so on, right? So these will all connect. So graph attention networks are in a way a strictly kind of a strict generalization of transformers. If you view transformers as they're operating over a graph that's fully connected. So this full connection is actually kind of problematic because in a graph that's fully connected, you have a quadratic number of connections. And so now if your sequence gets longer, then this quadratic number of connection grows quite quickly. Instead, in a graph, usually graphs are very sparse. So for example, molecular graphs, the degrees of the nodes are very low, and so you'll be computing much less, so you can remain much more sparse. Now, just to kind of go over how these attention mechanisms work, usually what you have is like, imagine I want to compute the attention with respect to a node, so let's call this like xv, and this node is like connected to x1 and x2, and maybe this node is connected to itself. Okay. Now what they do is they have a neural network, phi, that takes xv and like some of its neighbors, right? So we have like I in the neighborhood of v, okay? And this will be like your activation vi. So this is just a neural network, and all you can view this neural network is like this outputs a scalar value usually. And what you can do is like this network is pretty much just saying if this number is big, it's like saying that this node is very kind of important for this classification. So if it's putting like if like this kind of attention, like raw attention weight is very big compared to this one, then it means that in some way xi holds more information to xv compared to x2. Importantly, AVI in general does not equal AIV, right? So this is a way to encode asymmetry in this attention mechanism, and this is very important, right? Because if you're symmetric, you're pretty much saying if a connection is strong one way, it's strong in the other way. If you're asymmetric, you can break this symmetry. And this is why transformers work. If the attention mechanism in the transformer was symmetric, you would actually not learn anything because all the representations would be the same. Okay. So then what you do is you collect kind of all of these, you'd have like your AVV, you'd have your AV1 and AV2, and you want to turn this into a probability mass function this is for regularization, so that your stuff doesn't explode, right? But So in general, you kind of have all of these activations, and you want to turn this into a probability mass function. So what operation can I do on a vector that would turn this into a probability mass function? Does anyone know?
Softmax.
Yeah, exactly. So pretty much what you do is you run softmax on this, right? And now you get a probability mass function over node. Importantly, this can be interpreted as something known as a random walk, because now what you can, and a random walk is like pretty much you start at some node. Let's say we start at xv, and then with some probability, I can go in any direction. Now, since I'm softmaxing this, I can pretty much say that, for whatever reason, this is maybe like 1/3, this is, let me do like 1/2, 1/4, 1/4. So pretty much I'm saying, these are the attention weights I learned. With this probability, I can jump to any other node. So this forms like a Markov chain. And so maybe from xv, I sample and I stay at xv, and then I sample again and I go to x1, and so on. So graph attention networks and transformers in general, they kind of define a random walk over these graphs. So this is, I think, a nice way to look at these kind of objects. Now, I want to summarize, really, just recap most of the fundamental models and show you how they look like in matrix form. Because in general, when you want to implement stuff on a computer, you're not working with the message passing form. You still can, but you work with the matrix form of these operations. So let's start with GCN. So let's assume that X is like our original feature matrix, like X0. Now to get like xt plus 1, and the double underline means it's a matrix, right? So what I do is I apply some pointwise nonlinearity, so this can be ReLU. Then I have this factor. I'll explain it in a bit. I have xt and I have w. Okay. So let's decompose this. So here I am considering, these are all matrices, by the way. So let me just decompose it. So w, I guess wt, this is just a weight matrix, right? So this would be like d times d prime, for example. Xt is the features we have at layer t. And then this term is called a symmetrically normalized adjacency matrix. We don't use the normal adjacency matrix because it has spectral problems. So really, if you use the normal adjacency matrix, the spectrum of this matrix, so the eigenvalues, are kind of unbounded. Like as the graph grows, the eigenvalues grow as well. So this normalization assures that like the eigenvalues are between 1 and -1, if I remember correctly. So this is important because there's a connection here between this model and like this is a similar kind of line of thought in like recurrent neural networks. Like if you ever, we'll talk a bit about this later, but like in recurrent neural networks, if you have many layers, you get it in problems with like vanishing gradients or exploding gradients. And this happens when the spectrum of these matrices, usually of the weight matrices, is not well behaved, right? And this means that you can explode because you're kind of multiplying lots of matrices together. Okay, this is the GCN, and we call this like kind of the matrix form. Equivalently, we can write this in the message passing form. So here we consider V. So this is a vector now, and then we simply do this times the sum of like V connected to U of like 1 over the square root of dv du w x u. Okay. These two equations are exactly the same. The only difference is that this is V and this is V. The only difference is that in the top equation I'm working with matrices. In the bottom equation I'm working with like what happens at each node vector individually. So I hope this is clear. And then this 1 over square root of dv du comes from the specific normalization we're doing with these matrices. So if you remember, D is a diagonal matrix. So now if we're inverting this, we get 1 over D on the diagonal, and we taking -half, so it's 1 over the square root of D. So these are where these kind of factors come from. And really, you can view kind of many GNNs as like, this you'll see more in the practical, like you kind of think about how these different models relate to each other and how they relate to transformers. Yeah, so there's many other kind of normalizations we can take. I won't go through them, but then if we look at GAT, for example, we already know that like it's kind of the same. But now, like the only thing now we have like some kind of like lambda VU instead here, right? So this is the only thing that differs between a GCN and a GAP. So in some way, a GAP is only a GCN with different normalizations, but these normalizations are learned. But actually, learning these normalizations is extremely powerful. This is why transformers work well, because if you're learning a normalization, you're kind of saying, I can completely ignore the contribution of one vector for the kind of classification, for the latent representation of this current vector. Okay. Now we'll go a bit into like spectral theory of graphs and random walks. I mean, this is like very introductory, but it'll be kind of useful for what we want to talk about next. Okay. So again, we've seen this LD minus A. This is a Laplacian. And the Laplacian operator acts on node signals. And this operator quantifies how different your neighborhood is from you. And what we can do is normalize this. So remember this factor here. This is pretty much just saying that like we can take LD D minus A, and then we can just say like, okay, let me multiply both sides by half, as so. And then you get I minus this thing, yeah. So this is just a normalized version. Again, we do this to kind of bound the spectrum of this. So usually you want to work with normalized Laplacians and normalized adjacencies because this is just nicer. Now, in particular, all of these Laplacians, if we consider undirected graphs, such that if an edge goes one way, it goes the other way as well, we know that these matrices are symmetric, which means that the eigenvalues are real, and as such, we can order them. So usually it's common to order them this way. And a Laplacian is very important because you can define something known as like a Laplacian quadratic form. And really, this Laplacian quadratic form measures how smooth your signal is over the graph. So again, we have a situation where we have a graph and vectors attached to each node. We want to say how, over the entire graph, how different are these vectors locally. And it turns out that if you just take x transpose Lx, so this is just a normal quadratic form, with the structure of the Laplacian, you get something that looks like this. And to the right, I'm rewriting it as the gradient of over the graph, right? And this sounds maybe a bit confusing, but it's actually a really simple quantity. So if I have like some xv connected to some like xu, the gradient, I should draw my u's better. The gradient at vu of like x is simply defined as xv minus xu. So it's kind of looking at, if I go in this direction, how does my signal change? And intuitively, this gradient, since we're summing over everything and taking squares of it, okay, but this is just, squares are just like a detail, you're kind of saying, if this quantity is low, it means that over the entire graph, if I take little steps, then I never really collect much gradient, right? So I'm kind of moving along the graph, but the vectors never really hop around much. If this is big, then it means that your signal is not very smooth. It's like kind of very inconsistent across the graph and so on, right? So this is a very, very nice quantity to keep in mind. Now, in particular, as this quantity is always greater or equal to 0 because we're assuming real signals, we know that Laplacians are positive semi-definite. And one extremely important result of these Laplacian eigenvalues is the fact that the number of eigenvalues that are equal to 0, so the multiplicity of 0, tells you how many connected components there are in a graph. So if I have a graph, which is like, let's say this is G, and I have, one part here, then another part here, then I know that I will have two eigenvalues that are 0, okay? If we assume that the graph is connected, then only one eigenvalue would be 0. And we know that, since it's positive semi-definite, the next eigenvalue would be strictly greater than 0. And this next eigenvalue is probably like one of the most important eigenvalues in spectral graph theory and has like many names. So the eigenvector is also like kind of important. So the eigenvector, like let's say the graph is connected, then the eigenvalue will be 0. The eigenvector will be constant, and this is kind of like you can see it as like you're just trying to minimize that quadratic form, and to minimize that quadratic form, you just need to set all the kind now it'd be like zero, like it would be 0 squared summing over everything and you get 0, right? So this is like why the constant eigenvector is, at least for the non-normalized Laplacian, the eigenvector of eigenvalue 0. So yeah, so we're alluding like that the first eigenvalue is probably the most important eigenvalue. And this has many names, and usually when something has many names, it means it's like quite important. It's called like spectral gap, Fiedler value. Fiedler, I think, discovered this in the 1950s. So of course, all this stuff is like completely unrelated to GNNs, right? But now we will connect all of this back to GNNs later. And really, what we will see is that this eigenvalue tells you how well the graph is connected. So this is a very important eigenvalue. Pretty much, if this eigenvalue is big, it means that the graph expands well. So it means that kind of okay, there's like a theorem, there's a connection to random walks in this, but like pretty much this eigenvalue, like if it's a very small eigenvalue, we will see why this intuition is true. It means that this graph is kind of like not very good for graph neural networks. So it means that information struggles to travel across the graph. Okay, why is this true? We introduced something known as a Cheeger constant. So Cheeger constant is kind of trying to find, it's kind of related to like minimum cuts. And so like, let's say I have a graph, like something like this, yeah? What I do is I look at all partitions of the graph, so I kind of divide the node set into two separate sets, right? And then, like for example, I could look here, and then I kind of look at how many edges are between them, right? So I'm really looking at how can I most efficiently disconnect this graph. And yeah, and the volume is like just the sum of degrees. These are just like normalization factors. But the kind of all you need to know about this Cheeger constant, because I think the formulation there is not super intuitive, is that this represents the minimum energy you need to disconnect the graph, right? So if a Cheeger constant is big, it means that the graph in some sense is well connected. And if the Cheeger constant is small, then it means I can find a cut such that the graph disconnects easily. And really, when you have a small Cheeger constant, you say that the graph has bottlenecks. And I think this is a good kind of intuition. So if we look at this graph here, intuitively, will this have a small or big Cheeger constant? Yeah, so small. So this is a very small Cheeger constant because I can just draw a cut here and disconnect the graph into two communities. Instead here, the Cheeger constant is improved because this is probably still the best cut, but it has many more edges. So in some sense, the energy to disconnect this graph is higher. At the top here, you can see there's a lot of intuition that comes from differential geometry. I think the Cheeger constant actually comes from differential geometry, but there's kind of this, I think it's nice to think as graphs as like discretizations of manifolds, so of like surfaces. So here you can kind of see like a graph that's like has, you can really relate this to curvature, by the way. So like a graph that has like this area where you can cut the graph easily is usually an area with negative curvature, right? So this is another way of thinking about, don't worry, I really went through that quickly. But now probably, why have I been talking about spectral gaps and Cheeger constants and all these things? I'll tell you later because first I want to do this. So first I want to talk about like where oversquashing comes from. Saying that there's like bottlenecks, yeah? So in particular, these bottlenecks are very problematic for graph neural networks, and we can intuitively see why. So let's say I have a bunch of information here that I want to communicate across the graph, right? So I want to send this information into this other community, right? Now, all of this information has to pass through that one little edge. And this edge has only a fixed vector of information it can carry. But instead, the messages coming, and we'll kind of formalize this later, all the messages coming from the left community grow very quickly, right? So you have a lot of messages, especially as you take more message passing layers, and you're trying to fit them all through this one little edge. what happens is that you end up losing a lot of information. So this is known as like over squashing in some sense, but I mean this problem is really like a problem that like bottlenecks mean that information struggles to be pushed through along the graph. And this is why it can be beneficial to add these kind of virtual edges to propagate information through, or to allow the model to propagate information through with more easily. Now, I just want to take a step aside to talk a bit about recurrent neural networks. It'll be like quick, but like a recurrent neural network takes in a sequence. I guess you guys have covered them, but anyway, you take a sequence and you want to create some latent sequence usually, something like this. And the way it works is like, let's say I have like my x1, I feed this into like my recurrent neural network, I generate some latent sequence, and then I also pass this back to like my next step, and so on, right? So this is kind of how a recurrent neural network works. In kind of message passing form, let's say, this would be like kind of your xi is equal to some kind of sigma of like yourself. So this would be like xi minus 1 plus some other like matrix of like xi minus 1. Okay. Now, this is the exact same problem as in graph neural networks. So if you have a very long recurrent neural network, what happens is that you have, you're kind of trying to bring, like let's say you have like kind of very long of these sequence, you're trying to bring information coming from here all the way over here. And this is exactly the same problem. You have at each point a fixed size vector, and now you're squishing, this time linear amounts of information instead of exponential amounts of information. You're squishing them into a constant size vector all the time. So for this reason, people start to notice that recurrent neural networks tend to forget, right? So recurrent neural networks in a long sequence will tend to forget information that comes towards the beginning of the sequence. So this is why people started proposing bidirectional recurrent neural networks that kind of try to deal with this problem, but then they found out that these I kind of forget the middle bit, they forget like the endpoints, but then they started proposing transformers, right? Transformers kind of completely disconnect, like completely say, okay, let me connect everything with everything, and then you decide what's worth it, right? So this is kind of the intuition why over-squashing is like an important problem to study, because in graph neural networks, this is strictly the hardest version you can have of this over-squashing problem, because now you're kind of, the information you're trying to fit grows exponentially, while here grows linearly, right? So this is just to motivate why what we will be talking about is important. This is not only for graphs, but this is for many models, recurrent neural networks, transformers, and so on. Because again, even recurrent neural networks, you can view them as graphs, right? So as graph neural networks that operate over like directed graphs. Okay, if you remember the Cheeger constant, why did we mention it? It was mostly because of this inequality, which is like very important in like theoretical computer science and like graph theory. And it's like the Cheeger inequality, which pretty much relates the first eigenvalue of the Laplacian to this Cheeger quantity. And really what you can gain from this inequality is that this quantity is bounded above and below by this Cheeger constant. This means that you can really view this spectral quantity as a proxy for this Cheeger constant. And this is important because if you remember Cheeger constant, you have to consider cuts, right? So all of these cuts, right? But these cuts, there's so many of them. So in particular, computing this Cheeger constant is NP-hard, right? So it's not tractable for big graphs to compute the Cheeger constant. But we can definitely compute the first non-zero eigenvalue of a graph. This is completely fine. And in this way, when we're trying to like optimize the graph to allow for propagation of information, we don't optimize over the Cheeger constant, but we optimize over this first eigenvalue, and this we know how to do, right? So this is why I kind of introduce all these quantities and so on. Like they're kind of all related, and yeah. Now I'll introduce the last bit of theory we need, and then we can go on to like some theorems and results that to kind of get more intuition on what we're trying to do. So I kind of went over this, but like I want to talk a bit about random walks. So a random walk is really what we defined before. We have a graph, but now over the graph we kind of have probability distribution, right? So they go both ways. And so this probability distribution kind of tells you I'm at a step, let me sample a number, and then I'll jump to this next node with some probability, right? Yeah, usually what you do is you take like a very simple random walk, and this random walk is like the probability is just 1 over your degree, right? So a node will have a number of neighbors that's equal to the degree, and so if you take 1 over the degree, you're pretty much saying let me, with equal probability, sample and go to any of these neighbors, right? So this is kind of like a very uniform random walk over this graph. And really, you can view this random walk as kind of, you're just computing this matrix. So this matrix, if you take D inverse A, is literally like called the random walk matrix for this very reason. Like this matrix is encoding at every node 1 over dV, right? And with these random walks, I mean, people kind of spend their lives just studying random walks over graphs, so we're interested. So there's like a ton of theory, but we're interested in this notion of a commute time. And commute time simply means that let's say I have some node V, and kind of a lot of nodes here. Like there's like a lot of kind of stuff in the middle, and some node U. It's saying the commute time is quantifying what is the number of steps in this random walk, such that I go from V to U and back. So the expected number of steps, right? So intuitively, if these nodes are kind of nearby, this commute time will be quite small. But it's not only a function of the distance between the two nodes, it's also a function of the topology. So an extreme case is like, let's say I have like a very kind of dense area here in the graph, right? So maybe just like a clique, like this is extremely dense. And then I just have like a path, right? So I like to call this like the lollipop graph, because it's kind of like a lollipop, but you have like your node V here and your node U, right? Now imagine that this clique, Kn, n goes like very, very big, like n is very big, right? So this kind of lollipop part becomes like a black hole, right? Where like it's really hard to escape this clique, because remember that you have a uniform probability, so now your probability to escape this black hole is like 1 over the number of nodes, or -1 or something. But so in some, or +1, but like in some sense, if your clique grows very, very big, right, you are making the probability of exiting this black hole very, very hard, and as a consequence, your commute time will become very big, right? So in some sense, your random walk gets stuck in that situation, and for this reason, it's not only a function of the distance, because here I'm not changing the distance between the nodes. I am just simply changing the kind of how many nodes there are and like the topology of the graph, right? But the distance between V and U remains the same if I'm not touching the path. And here's a plot of like how modifying the graph kind of affects the commute time. So here there's like a node of reference, and I'm computing the commute time with respect to every other node. So you can see that reaching nodes here is like pretty easy, the commute time is very low, but then reaching nodes here becomes very hard. So the commute time becomes like 175. So the expectation of going there and back is 175, even though the diameter is much, much smaller than this, right? So this really kind of gives intuition for like how these commute times tell you how kind of easy it is to kind of travel across a graph. And now here, what we do in this graph here is we connect every node that's within a 2-hop radius, right? So the graph obviously gets many more edges, so we say that this graph is more dense, but the commute time gets pretty low, right? Like much lower than 175. But here on the right, we only add 2 more edges. We only add this one and this one, right? But then you can see that the effect on commute time is like kind of very similar, right? So in one case, I'm adding almost no edges. Like I'm only adding like very kind of targeted ones. And in the other case, I'm adding is really saying something interesting. Like it's saying we can improve the information flow on this graph without touching it too much. So the information, what we will show later is that, I guess maybe you can read our paper, but like pretty much what you can see is like you can like mathematically connect how well information propagates with a graph neural network to the commute time directly. So really this commute time is like a very important quantity for intuitively understanding the propagation of information. Fortunately, the commute time is tractably computable to some extent. You just need to invert the Laplacian. Okay, pseudo-invert the Laplacian, right? So it's kind of interesting. This stuff is actually related to electrical circuits. So people started kind of looking at these quantities because they realized that they are kind of related to like resistors and these things, and then people also connected them to like random walks. So kind of interesting. And now we can talk about issues in message passing neural networks and how to fix them with like kind of the stuff we just talked about. So the first issue is oversmoothing, which I think you have heard about. What I want to show is the relationship of oversmoothing by looking at partial differential equations. So consider this heat equation. So a heat equation, if you're not familiar with it, is like kind of an equation that this was like analyzed by Fourier like in the 1800s or something. And it's kind of saying, describing how heat kind of evolves in a closed system. And we can really define a heat equation over a graph the same way. So you can view like a graph now, you can view like a graph now, your heat becomes like your node signals, right? So the temperature at a node is like your node signal, and then you evolve this by multiplying it by the Laplacian. Now, what I will show you now is that graph convolutional networks are discretizations of this heat equation. So we take a very simple discretization. So this is like the first order Euler discretization, and we take a unit time step. Okay, and so pretty much this is the discretized version. This goes to 1, and then we can move the xt to the other side to get this. Okay, and now we can factor out this like the identity matrix. And now, okay, let me just go through it maybe. So we have LD minus A. The normalized version is I minus this. And then, pretty much if I rearrange, I get that, so I get that this is equal to I minus this, okay? And now I can plug this into here, and I get this. Now, this is exactly a graph convolutional network. If we add a nonlinearity here and a weight matrix here, right? So if I do this, this becomes a graph convolutional network, okay? So really, we can see how graph convolutional networks relate to heat equations. In some sense, it's a discretization of a heat equation where one layer of a graph convolutional network is like one step in time in this discretized differential equation. Why is this important? Well, as we all know, heat tends to become uniform in a room, right? So in a closed system, what happens is like heat eventually will become constant. Mathematically, you can view this as heat. This PDE minimizes the Dirichlet energy. The Dirichlet energy we went over before. This is the same Dirichlet energy, just in matrix form. So now, before we consider Dirichlet energy in like you have scalar signal over the nodes, now you have like a vector signal. So before here we had vectors, now these are matrices, but it's the same exact quantity. And since we know that kind of these PDs minimize this Dirichlet energy, we can say that in some sense, graph convolutional networks, as you apply more layers, minimize this Dirichlet energy. And why is this important? Does anyone have an idea of like why is this a problem? So maybe the intuition here is that this Dirichlet energy tells you how smooth your signal is. So why is it bad if a signal is very smooth? Does everyone know? if you have a very deep graph convolutional network, you're getting very smooth signals. At the end of the day, your nodes lose their information, right? So you kind of end up getting a constant signal up to some like node degree information, maybe, depending on the normalization, but this is very bad for learning, right? So in this sense, this is kind of shows why graph convolutional networks cannot be built very deep. And you may ask, why do we care about building deep? Because in general, in representation learning, like in convolutional networks or these things, you want to build deep models because these seem to work better. But we have kind of just shown in some like heuristic manner that it's very hard to build deep graph convolutional networks. This is not to say that you can't build deep message passing neural networks. People have kind of found some solutions, but the basic standard graph convolutional network won't work deep, with some asterisks there because it depends on the eigenvalues of the weight matrix. But yeah, so this is just what I said. Okay, so this is one problem. This is over smoothing. The fact that kind of the node signal, as we go more deep, becomes smooth. Okay. Now we'll talk a bit about over squashing. And now this I'm kind of going into a paper we just published in ICML. So this is kind of like very recent. I mean, ICML is still to happen. So this is like super recent work. So yeah. Consider this message passing neural network. This is like the same neural network we saw before. Just added these two factors, but this is just notational convenience. Like, of course, you could absorb these into the matrix. Like, this is the same, but just for kind of notation. So in some sense, the CS and CA tell you how much weight you're giving to CS and CA, or to like the self loop and like your neighborhood factor. And then let's look at this matrix here, right? So this is like, again, notational convenience because these bounds get a bit like messy. What we want to see is, oh yeah, just a remark, this like a lot of the message, like famous message passing neural networks, again, fall under this, but we kind of move through this. Now, what I want to show you is that there's another problem alongside over smoothing that arises, and this is called over squashing, and this is related to recurrent neural networks, but I just kind of want to formalize it a bit more. And really, this over squashing, it's defined as like, you look at this partial derivative. Yeah. So, what does this partial? Okay, my writing is really bad. XV. So, what does this partial derivative tell us? And we made this a bit mean question, but does anyone want to have a guess? So, just for notation, sorry, maybe I should. So here we have some node U at the layer 0 of this graph neural network, and here we have some node V at the layer T. V and U are different nodes. So what is this partial derivative telling us? Yes, but at different layers, right? So exactly. So this is telling us at a specific layer of our graph neural network, how does the initial signal at node U affect our final signal in that representation? Okay. Now, intuitively, if this is small, if this quantity is small, right, it means that kind of XVT is like not highly kind of affected by XU0, right? And if it's big, it's like opposite. Excuse my handwriting. But this is kind of the intuition, right? Like if you have a high value for this, it means that node V is sensitive to node U, right? Even after many layers. Instead, if it's not, then this is bad. What we will see now is that this quantity can really characterize intuitively what we think of as over squashing. So this is like the same phenomenon as recurrent neural networks. Intuitively, we expect that like if we're in a recurrent neural network, this partial derivative, if we're considering like a node, like V in this case would be like at the end of the recurrent part, and U would be at the start, then we know that this derivative will kind of decay, right? So in some sense, this is the intuition behind this quantity. consider an MPNN with m layers and a width p. So p is the hidden dimension of this graph neural network. And sigma is the Lipschitz constant. So I think Jacob mentioned this, but the Lipschitz constant tells you a bound on the derivatives of this function. So if a nonlinearity has big Lipschitz constant, it means that this is quite a, like at some point there's a big derivative somewhere, right? In general, Lipschitz constants of nonlinearities are like 1, right? So with ReLU, the Lipschitz constant will be exactly 1, right? Because the highest point of the derivative of ReLU will be 1. Okay. Now, what this theorem tells us is kind of interesting. Now, in this side, we have contributions given by the model. So, in some sense, what we see is that this partial derivative is bounded above, and this depends by two kind of quantities, the model and the graph itself. So, if we have high hidden dimension, then it means that this is a good thing for oversquashing. Intuitively, we're trying to fit information in a bigger hidden dimension vector, and so you have more room to not lose this information. At the same time, W is the maximal, is some kind of norm on the weights, right? So also having a big norm on the weights intuitively makes sense that you're more sensitive. And similarly, intuitively, if you have a high Lipschitz constant, it also makes sense that you're more sensitive, right? Because all of these things are kind of making functions that are more, that change with like more violently. Okay, maybe violently is like a strong term, but like, you know, they change, they're more sensitive to inputs. And now here we have the topology. Now, if you remember, this S is like something like kind of Ci plus Ca. I believe this was the notation. But it's pretty much just a combination of it's pretty much like an adjacency matrix with self-loops. So if you add to an adjacency matrix a diagonal matrix, you're kind of adding self-loops to each node, so the nodes can kind of talk to themselves. And intuitively, if it's normalized, this stuff kind of, in some cases, goes to 0, right? So, or at least decreases, right? And you can view this as like a random walk, right? So if you take powers of random walk adjacency matrices, they actually behave quite nicely. They're saying, what's the probability of reaching distant nodes, right? So in particular, maybe I can write it up here. So I have A, right? A tells me how, like, what walks there are from, like, node, like, between neighboring nodes. Let's say now I take powers of A. So I take A to the K, and I look at nodes V and U. This will tell me the number of paths of length K from V to U. Okay? So this is just like if you carry out the multiplication, maybe this is a nice exercise. Multiplying these, oh yeah, I guess you can see it because it's, let me move it. So, A to the K tells, the entry VU of A to the K tells you how many paths there are between V and U and length K. So in particular, if the distance between V and U is bigger than K, this is always 0. If not, then this number really grows if you have self-loops. That's a technicality, but okay. So intuitively, if you normalize now and you have random walks, this really tells you what's the probability of me going from V to U, right? So this is the intuition. And if nodes are kind of far, right, and like your graph kind of spreads out, this probability will get smaller, right? Because you're kind of landing in different parts of the graph. So in general, this bound tells us that like how sensitive we are from U to V depends on the model and the graph itself. We will do some experiments later to show how this kind of affects it. But this is very important because in general, if this quantity decreases, then we're in trouble, essentially. Now here's like a synthetic experiment which we did, and this is kind of really to validate our theory. So the idea here is that you have, so you have a source node and a target node, and all of the other nodes are complete like noise. And what you want to do is copy with a graph neural network the information from the target node expect that like this becomes harder as these graphs grow. And what we can do is we can actually analytically compute these this quantity based on the powers of the adjacency matrix. And theory tells us, given our bound, that we can actually order them like based on how hard they are. So cross ring will be the easiest, ring will be the second easiest, and clique path, which is the lollipop graph I was talking about before, is the hardest. And again, we're just inferring this from purely the topology of the graph by looking at powers of these adjacency matrices. And this is the result. So at the top, each graph is like these different synthetic paths. And at the bottom, first we're exploring the hidden dimension. So again, if you remember in our theorem, the first term, like we're pretty much upper bounded by some quantity that was like the Lipschitz constant of the nonlinearity, the width, and the norm on the weight, and the hidden dimension. So intuitively, if we increase the hidden dimension, we should do better on this task. And this is exactly what we see. We see that like consistently, the higher hidden dimensions help us solve this task. Intuitively, this is like saying, if you have a higher hidden dimension in a graph neural network or in a recurrent neural network, you're able to resist this effect of like your sensitivity decaying for longer. Again, this makes sense because you have more, it's like having a truck and you want to carry packages, and now you have more room to fit your packages in the truck, right? So now you can kind of carry packages for longer if you're like a delivery driver. And here we have, instead now we're plotting for different models the performance on this task, growing these synthetic tasks, but kind of on the same task. So you can see that really our bounds are completely respected. So the clique path was the hardest, and the performance drops off consistently for all these message passing neural networks. So really what we have shown with this theorem is that kind of we can relate this stuff, like we can really study these networks formally and get a good intuition for like how they will behave in practice. So obviously these were synthetic tasks, but these give you some intuition how like kind of the topology affects the problems, right? So really the first plot shows us how the architecture affects the problem, and the second plot shows us how the topology affects. So there's kind of this interplay between the topology and the model's architecture that you can play with. Maybe I'll go quickly through this. How much time? I have like half an hour. Okay. So now let's see what happens if we go deeper in a model. Again, maybe going are exactly at distance k, right? And now you take a number of layers that's greater than k. Now the number of paths between v and u grows, right? Like in some sense, taking the model depth exactly at k is the worst case scenario for this transportation of information, because you have very few paths between v and u, right? So this term here is like the number of paths, right? So sometimes if you go further than the depth of the, like if your depth goes further than the distance, it's kind of like I imagine like kind of a wave, like in some sense, originally like your wave just reaches like your feet or like this barrier, but then if your wave kind of goes much further, then it will kind of like explode, right? So in some sense, this is what's happening. The information, if it's just reaching, it's kind of not really doing anything, but if it's going much beyond, then it will like cause havoc or something. I don't know. So this is just what this bound is saying. I mean, there's more terms and more components, but the main idea is that like, this is the intuition. But really, we enter into another problem, which is very kind of well studied in machine learning in general, but people first, again, thought about this in recurrent neural networks, this phenomenon of vanishing gradients. So vanishing gradients is when, effectively, when you're training a very deep model, it's very hard to do this, because in some sense, if your matrix, if your spectrum is not stable and so on, your gradients tend to either explode or go to zero, right? Because you're kind of multiplying lots of stuff together, and this is not easy to do. So this is very unstable. So in some sense, going deeper is good in GNNs, but going too deep is not good, right? So perhaps there's some kind of sweet spot of how deep your model can go to avoid a lot of these problems, right? But still kind of look at long-range interactions over the graph. And here, I guess we can develop like a kind of phase transition model. So when the number of layers is less than the distance, we're completely insensitive, right? So this makes sense because the two nodes never get to communicate with each other. Again, in message passing, you're exploring one neighborhood hop at a time. If you're not doing enough hops to reach that node, then you're completely insensitive. If we reach the case where our depth is exactly the distance, then we get over squashing. Again, this is kind of this wave analogy. We're just reaching it. This is not good. If we're like slightly over, this is probably the best case scenario. And instead, if we go much over, we run into like vanishing gradients, over smoothing, and all these things. So it's actually, I mean, there are these problems. Like everyone's talking about, like like it's hard to train deep neural networks. Probably in practice, it's not necessary because you can get away with some training tricks as well. Like if you use like batch normalization, these things. Like to train neural networks that explore a good portion of the graph and do not run into these issues, right? And this is kind of what our theorems show. So yeah, so if you have a small diameter, you're in I mean, even massive social networks have really small diameter, like surprisingly small diameter. Choosing a number of layers that's like slightly bigger than diameter is probably like a good idea, right? Obviously, if you're in a big kind of chain of molecules, then like you can't do this, but yeah. So these are just the takeaways. The model architecture, the topology, the depth. These are all kind of related to like over-squashing and all these things, as we've shown. And commute time, so these kind of spectral quantities also. I mean, in our paper we have this kind of theorems that show this, but like commute time is also like a very important quantity. Okay, now I will attempt to like connect everything to transformers. Not necessarily just transformers, but I think this is like a nice perspective on graph neural networks in general, so can go through it. Now, we've spoken about changing the graph, right? So we want to, in some way, modify the graph such that the information can propagate better, right? So this is the main idea. And we can formalize this by saying we have a map, R, that takes kind of an adjacency matrix and gives you another rewired adjacency matrix. So this kind of acts on your topology and changes your topology, right? Based on some heuristic that you may care about. For example, you can try to maximize the spectrum with this map or something given a budget. Now, intuitively, if we control this adjacency matrix, it's kind of like we're controlling this matrix value that came into our bounds before. So intuitively, we can use this to directly improve the bounds on over-squashing. Usually, though, most rewiring techniques compute a single rewiring R, and they can look at like improving the Cheer constant by maximizing the spectrum or things like this, or maybe you can lower the diameter. You can really view transformers as having a really kind of simple rewiring map where you say, let's fully connect the graph, right? So we make the diameter of the graph 1, and from this perspective, transformers are kind of taking the most kind of simple and like kind of dumb approach of like, let's just connect everything with everything. We won't have all these problems because now, these are just simply not problems. They want to do one layer and everything is done. Yeah, you can still use many layers, but this is kind of the intuition. Now there are a few issues. Like let's say there are a few problems that come with like taking an arbitrary rewiring map, and namely like consistency and density. So we call this like spectral rewirings and spatial rewirings. Transformers fall under spatial rewiring, so they have obviously big problems with density. Spectral rewirings are what we saw before, where we can add one edge that just like kind of looks at maximizing the spectrum most violently, but then this has an issue of consistency. And maybe I'll draw this now. So let's say I have a molecule, and it's like a very kind of small molecule, right? And I want to do a rewiring. And all I do is like I try to maximize the spectrum. So this means I will add an edge, maybe that looks like this, okay? chain of molecules. So, like imagine it's another molecule, like these are all kind of, it's like a big chain. And now my rewired edge will look something like this, right? So I'm just trying to maximize the spectrum on this, the spectral gap on this graph with a single edge. If I do this like with a spectral rewiring, so let me just write this like spectral. Like what happens is that pretty much the same rewiring policy completely has different effects depending on the graph, right? So if you have a very kind of small little molecule, it will rewire in one way. If you have a very big molecule, it will rewire in a different way. And we argue in like a recent work that like this is very inconsistent, right? So a model will likely generalize poorly to spectral rewiring. The flip side is like, let's say I have like a, this massive molecule here. So let's say I have this kind of molecule, like let me just draw a square. And let's say I'm a transformer now, and so this is like a spatial rewiring. Then what I'll do is like I'll kind of connect everything with everything, yeah? So this is like spatial. In some sense, both are bad, right? Like at the top, you're being completely inconsistent, so you get generalization issues because, like, how can your model learn over this? And in the other case, I'm becoming quadratic in the number of nodes, right? So this is also extremely problematic to train a transformer or something, because you simply cannot do transformers on very big graphs because they won't fit inside a GPU at all. This is more like a kind of diagram in our recent paper, but like the basic idea is the same. So in spectral rewiring, we're adding very distant edges. In spatial rewiring, we're becoming very dense. And in our technique, we kind of say, well, let me define a connectivity measure, mu, and a locality measure, delta. So this mu here, this delta here, is simply saying how this, you can simply view it as like how local are these nodes, right? And this mu kind of fixes this inconsistency, right? Because now I can kind of have this system where I can deal with nodes at different distances in different ways. I'll show you how later. And this connectivity measure instead tells you which nodes should I prioritize. So intuitively, on this kind of like diagram here, these nodes here are already kind of well connected, right? So it doesn't really make sense to waste an edge if we're trying to add as few edges as possible to connect nodes which already have many paths that reach them. Instead, we want to connect edges in structures that look a bit like trees, right? So we're kind of like prioritizing for remaining sparse by adding edges only in parts of the graph that need them most. And at the same time, this delta allows us to remain more local. And really, you can view this as like a dynamical system. So you start with some base graph G0, and then you evolve it with some rewiring maps G1, and so on, until you reach some like G stars. And G stars like your most favorite graph in the whole world related to G0, right? So this map has to be equivariant and so on to respect the symmetries. But this is the basic idea. And now what you can do is, you can say that, well, this is like A0, this is the adjacency matrix with like the original graph, this is the adjacency matrix with like A1 or G1, and this is like A star, that's called this like AK. And now we can run something known as like, we can construct a graph neural network that kind of operates over these adjacency matrices separately. So intuitively what you can do is like say like your node V t plus 1 gets updated as like the sum over all of the k's, so over all these rewirings, times the sum over all of these, over all the v connected to u, of these wk t's x u t. Okay? are probably like the best graph in computer science. And I don't mean this from like they're beautiful, but I mean this from like their properties. So again, expanders are, well, spectral expanders really, but they're graphs that have a big lambda 1, but they're still sparse. So intuitively, does anyone know why this is a good thing? Why would you want a big spectral gap and be sparse? So again, the spectral gap tells you how connected you are, right? So why is this good? Okay, so effectively these, you can view them as like approximations to fully connected graphs, because they have very good, they're actually the best possible fully connected graphs that are sparse, right? So really, this big spectral gap means that your graph is very well connected, but the sparsity means that that you don't have many edges, right? So in particular, you have a number of edges that's linear in the number of nodes, okay? So you really have a graph that looks like this. So you have very few edges, but actually information propagates very, like, surprisingly fast in this. Theoretically, they are the graphs that have the best mixing time. So the mixing time means that if you take random walks, they will converge the distribution of random walks will converge very quickly to the uniform distribution. And of course, fully connected graphs have this property, but these are not quadratic in the number of edges, right? So this is like very useful. And in these sparse transformers, they're pretty much just saying, let's use graph theory, let's replace this fully connected graph with graphs in graph theory that we know are like very beautiful and like kind of have all the properties we nodes are kind of standard in transformers. Pretty much in a virtual node, what you do is like you add an extra node where all the nodes connect to it. So this is like very, well, it works surprisingly well. It's kind of, you can view it as like adding this virtual node is kind of like adding a memory bank to the transformer, and it can kind of read and write from this memory bank. And then in D, we simply overlay all of these systems together, and now we get a transformer that has density OV plus E. Yeah? Because this is like also O, but this is like actually like just V. This is O of P, and then this is like O of E, because it's like the original graph here. So you get a transformer that's effectively linear now, but that has very nice spectral properties. So this was just to kind of motivate why we care about this line of work. Like, you know, I talked to you about like for an hour and a half about like all these eigenvalues and like, okay, like this is cool, I guess, but like, I mean, this is actually like extremely useful not only for graph neural networks, but for intuition on like a lot of models, right? Because this is just a transformer. I mean, if you remove this like original graph part, then this literally becomes just like a sparse transformer that's like linear, right? But like in some sense, optimally linear, right? So it's very nice. I'll just leave you with some key questions, and then yeah. So the real question is like, do we even need many layers? Because a lot of people say that with GNNs, you know, like you can't get them deep. In general, you probably don't need to get very deep with these GNNs, right? So this is like, in general, the inductive bias given by your graph neural network is strong enough that like, in a social network, probably to predict which user this person should be friends with, you only need like a couple hops, right? Like you don't need to explore very far. Maybe in molecules, you need to in some way like get a bit further, but even then, depends. In recommendation networks, you know, usually you don't need to get very far. So really these problems are theoretical, they're very useful to study because you want to understand these models, but you know, in practice, this doesn't mean that neural networks or graph neural networks are not useful, right? Like actually they're used like in a ton of problems, and you don't need to go like 100 layers deep like people do in recurrent networks. Should we just use transformers inside graph neural networks? I think no, because transformers are very dense, and I don't don't like them so much. Well, I mean, I like them, but like I think it's kind of sad to throw away the graph in some sense. And I think a very nice question, but like really hard, I think, and I've been trying to do it for a year, but it's very hard. Can we learn a rewiring? If someone has a good idea, let me know, because this seems very hard. And how can we build optimally sparse transformers? I think it's a very interesting question because, you know, we have all these large language models now and things like this, and like they're all usually like bounded by how big of a sequence they can consider. But in reality, you know, if you can build sparse transformers instead of 2,000 tokens, you can build 10. I mean, for example, these Xformer papers, they fit 10,000 nodes in the sequence, and like not even on like the A100. So yeah, sometimes I think these are interesting questions, and yeah, there's my email and my Twitter, and yeah, thank you all for listening. Yeah.
So we said that the Ziegler constant helps to disconnect the graph, right? So what's the advantage of disconnecting the graph?
Yes, so actually, the Ziegler constant is like saying we don't want to disconnect the graph, right? Like if we're able to easily disconnect the graph, then it kind of, or like in general, if the Ziegler constant is low, it means that the graph has two big communities and very few bridges between them, right? So you can think of it like you have two football teams, right? Like the military police football team and the military football team and the police football team in Nepal. People probably don't talk to each other, right? And so it's like kind of like two communities, and maybe a few people are both military and police, and so they talk. So this would be a graph with a very low Ziegler constant, right? And in general, this is bad for, we don't want to disconnect the graph at all, because of course in a GNN, if you operate over a disconnected graph, then the nodes will never communicate with each other, right? So we definitely don't want to disconnect the graph. We just want to avoid bottlenecks in the graph.
In dynamic graph rewiring, is the summation over K actually done for all the adjacency matrices, or is it optimized in some way?
Yes, so really what you do is the adjacency matrix at like layer K is the difference between layer K and K minus 1. So this becomes like a very small, like very sparse, and now this becomes like very efficient. Yeah, I didn't want to like throw in those details because, but yeah, good point.
Okay, awesome. Thank you so much, Mr. Federico Barbero, for your time. I'd just like to welcome Mr. Simon. We'll just give a token of love to Mr. Federico Barbero on our